all of those in attendance for coming all the way to Japan to participate in this conference. So my talk will be about implementing supersingular isogeny cryptography, and I'll be talking about this with a particular focus on embedded platforms and sort of low-power platforms, which is not usually the kind of platform that you would think about when you're thinking about implementing isogenies, because isogenies have a reputation for being something that are relatively computationally heavyweight, so to speak, and they take too long to run on embedded platforms. Is sort of the conventional wisdom. This conventional wisdom may be best summarized by certain papers with titles such as these: 18 seconds to key exchange, blah 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 blah. Okay. This particular paper is sorry, it's a little subtle here. The reference is up here. It's the IACR preprint number 932 from this year by Copperman et al. And I'd like to sort of draw your attention to a few things. I quoted a small section of the abstract of the paper, and so their results are they implemented supersingular isogeny Diffie-Hellman, SIDH. And by the way, this talk will be entirely focused on SIDH, even though by now there are other things that you could call isogeny-based cryptography or even supersingular isogeny cryptography. That would not be the focus of this talk. I would just talk about SIDH, which is kind of the thing that I proposed way back in PE Crypto 2011. Okay, so they implemented SIDH on various constrained platforms such as a ARM Cortex M4 and a 16-bit microcontroller, and the number from their headline, which says 18 seconds, is their sort of performance number that they got on the ARM Cortex M4, which is a 32-bit processor. They could have put even worse numbers. There is an 11-minute figure for key exchange on the 16-bit microcontroller, but they decided to go with their best result, which was 18 seconds, and put that in the title. What really puzzles me is sort of the last part of the next sentence. It says, well, those results show that even with an improvement by a factor of 4, SIDH is in fact impractical for small embedded devices. Now that I respect as a matter of opinion. But the next part is, regardless of further possible I cut out the next line, improvements in performance. That's what it says. Okay, so I see to go, really, regardless of any further possible improvements in performance, like, isn't that the whole point, right? If you make it, surely if you made this thing 10,000 times faster, then it would be practical for small embedded devices. I mean, that's the whole point, right? Is to make the performance better. Look, I'm not trashing their work. I think it's quite well done, except for that line, which I'll just chalk up to maybe a misstep or perhaps non-fluency with the English language, I guess, or whatever. But certainly, if we could get further improvements in performance, then I think it would be in the conversation. That's the whole point of doing such comparisons, right? Is you're going to look at performance. Okay. So now keep in mind this other phrase, with an improvement, even with an improvement by a factor of 4. Okay, because we're gonna come back to that a little bit later. So I'm going to take a small detour to sort of introduce, roughly speaking, the idea behind SIDH. Perhaps not everybody here sort of knows everything about isogenies. If you're coming from a traditional ECC background, you may want to keep this overview in mind as I go over it. So in SIDH, what you do is, instead of using sort of discrete logs and scalar multiplications and so on as the basis for your crypto system, you're going to use isogenies and sort of the kernels of isogenies in your crypto system. Okay? So in SIDH, you have public parameters, which are analogous to in regular Diffie-Hellman. You have your public parameters, which are your group and a generator or an element of the group. Right? So in SIDH, similarly, you have a public parameter, which is just a starting point. This public parameter is going to be a supersingular elliptic curve E defined over a finite field. That finite field will have some characteristic p, and it will be a degree 2 extension over the base field. So it will be a finite field of cardinality p squared. Okay? So your public parameters are going to be the starting curve E and the prime P. To do the key exchange, Alice is going to choose a secret key. That secret key will be a kernel. Right? So Alice will choose a kernel, which I call capital A. The kernel is a subgroup of the elliptic curve. Right? It's a subgroup of the set of points on the elliptic curve defined over fp squared. So this kernel, where's my pointer? Here, this A, this capital A is the secret key. It is a subgroup, which means it is an entire set of elements. But of course, we don't write out this, we don't represent this kernel by writing out the elements of the set exhaustively. That would take too long because this kernel has cryptographic size as a set. What you do is you pick a generator of the kernel and you represent the kernel using that generator as a generator as a group. Okay? And so you do the same kind of thing for Bob. Bob picks a kernel, which I call capital B, represented by a point or an element that generates the kernel as a group. And that is Bob's secret key. The sort of public key corresponding to that secret key is going to be what I call the codomain of the isogeny. So there is an isogeny from E to what I call E modulo A. You're going to take the curve E and you're going to mod it by A. You're going to annihilate everything in A. And that sort of process gives you a group holomorphism. Isogenies are group holomorphisms. They're a bit more than that, but that doesn't matter for this talk. They're just group holomorphisms that sort of map one elliptic curve to another. And so E mod A is another elliptic curve. It is the unique elliptic curve up to isomorphism, supporting an isogeny from E to that curve with kernel equal to A. Okay? And similarly, E mod B is the unique elliptic curve emanating from E with kernel capital B up to isomorphism. Okay? So the secret keys are the kernels A and B. The public keys that you use in the key exchange are going to be the sort of values of E mod A and E mod B. So those elliptic curves are your public key. And there's a little bit more in your public key. You need like auxiliary points and stuff like that, but that doesn't actually matter for anything that I'm doing in this talk. Okay? So just keep in mind that the core operation in SIDH that we're going to talk about in terms of performance considerations is given a kernel A, compute the isogeny that goes from E to E mod A. Okay, that is what we're trying to do. So classically, there are formulas for doing this. Those formulas are called Veilleux formulas, or Veilleux's formulas after Veilleux, who discovered this and published it in 1971. So the formulas look like this. It's some big complicated mess. The only piece of notation that you need to bootstrap this is, well, I guess you need that A4 means the A4 value of the short Weierstrass equation for E, the domain curve. And then you need that, the set S, this set capital S here, is the set of all points in the kernel, excluding the identity point, and then modulo plus or minus. Okay? So you're going to take for each equivalence class of points up to plus or minus, you're going to take one representative of that equivalence class, and then you're going to smoosh them all together, and that gives you a set capital S. And this set capital S is going to be then used in Veilleux's formulas to compute your kernel. Now this is the mathematics. Of course, as I'm sure you're well familiar with, if you have any experience at all implementing just normal ECC, right? What you do when you're implementing this stuff is you take the formula that you get from mathematics and you try to sort of reorder the arithmetic operations in some way so as to get some sort of low complexity arithmetic formula that gives you the same results as the sort of theoretical formula, right? So you do the same kind of thing here. And I'm not going to talk about how to do that because that's the same thing that you do for traditional ECC. Okay. What I am going to talk about is you have to do something to break up the isogeny computation, and there is no analog to this in sort of traditional ECC. Well, there kind of is. There's square and multiply, or double and add, which is, I guess, the closest analog in traditional ECC. So the point is that when you have one big computation, like in traditional ECC, alpha times a point, right, where alpha is a number of cryptographic size, You can't just do, p plus p plus p plus p dot 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 plus p alpha times. That would be way too slow. Right, so what you have to do in traditional ECC is you have to sort of double p, you get 2p, 4p, 8p, 16p, and so on, and then you use binary, it's the binary representation of alpha somehow to get yourself an efficient combination of powers of 2 times p that add up to alpha p. Right? Of course, I'm way oversimplifying, but that's the idea. And so here you have to do a similar kind of thing. If your isogeny has huge degree, or even cryptographically large degree, which is sort of huge by ordinary standards, not cryptographic standards, of course, then what you have to do is you have to break up the isogeny into smaller pieces. Okay? And the way to do that is to factor the size of the subgroup, I guess, right? And of course, not every subgroup, has a size which is amenable to factoring. But if you're implementing this, you would choose a subgroup whose size is amenable to factoring. And in SIDH, what we do is we choose subgroups which are a size equal to a power of 2, let's say, or a power of 3, or something like that, right? So I've got on this slide sort of the general case where the subgroup has size equal to a power of L, where L is some small prime. L is typically 2 or 3, but it could theoretically be 5 or 7 if you wanted. Okay? And just sort of by way of illustration, I've got an example here where the power of L is L to the 6th. Okay? And I will sort of show you or walk you through how to construct an isogeny of degree L to the 6th without doing L to the 6th computations. All you need is 6 computations, each of size L, instead of 1 computation of size L to the 6th. Okay? So what you do is you start from you start from your generator, I guess, for the kernel, right? So R0 is going to be your generator, and the point is that R0 has order. R0 has order L to the. Did I misspeak? L to the 6th. I think actually in this example R0, L to the 6th. It has order L to the 6th. Okay. So what you're going to do is you're going to multiply R0 by enough sort of powers of L to get down to sort of something, sort of one thing, like a thing over here, which has order L. And actually, maybe I should stop here and let me try to get this right here. If I want L to the 6th times R0 to have order L, then I guess R0 is going to have order L to the 7th. Is that right? Yeah, so I guess I'm computing an isogeny of degree L to the 7th here. Okay, let's see how this goes. So I multiply R0 by enough powers of L to get down to L to the 6th times R0. This point has order L. So I can compute sort of isogenies, with this kernel, okay, with kernel generated by that point. So if I do that, then what I'm going to get is I'm going to get an isogeny which I will call phi sub 0. Okay, so that is the sort of 0th point. Phi sub 0 is an isogeny of degree L starting from E. And the kernel of phi sub 0 is this point right here. It's L to the 6th times R0. Phi 0 has degree L. Okay? Now, once I figure out what phi 0 is, and I do that using Belouv's formulas, right, which is not too bad because this isogeny only has degree L, and L is a very small prime. Okay? So once I do that, then I have phi 0. But I'm not going to just sort of write down the equations for phi 0. I'm going to use phi 0. Right? So I'm going to use it in the next step. It is an isogeny, right? And being an isogeny, I can evaluate that isogeny on points, right? So I can evaluate that on this point, for example. And when I do that, I'll get a point L5 times R1. What is R1? R1 is phi 0 of R0. Okay? Isogenies are group homomorphisms. They are linear with respect to scalar multiplication. And so whether or not I do it this way or this way, I get the same value. Okay? So now I have a point here, L to the 5th times R1. You can check that this point has order L. Right? If I multiplied this by L, I would get the result of multiplying this by L. I would get phi 0 of L to the 7th times R0, which is phi 0 of the identity, which is the identity point. Okay? So now this point has order L, which means that I can evaluate sort of, I can take the kernel generated by this point, all right? And then I can take the isogeny whose kernel is generated by that point. That isogeny will be phi 1. Okay? And what I've suppressed here from this diagram, because otherwise it would get too complicated, is that as you go this way along the diagram, so as you go from here to here to here, as you take slices this way, all of these points lie on your original curve, all of these points lie on the codomain of phi 0, all of these points lie on another elliptic curve, which is the codomain of phi 1. The domain of phi 1 is the codomain of phi 0, and so on, all the way down here. Okay? So you follow this tree, and you end up playing a sort of combinatorial game. Right? What you have to do is, this is all old stuff, but you have to understand how it works in order to follow what I'm going to talk about later. Right? So the combinatorial game is that you can go southwest freely, but in order to go southeast, you need to reach the endpoint, the green endpoint, sort of corresponding to the slice from which you want to take a further southeast step. Okay? So I need to reach this green endpoint before I can evaluate these 3 red edges. And then I need to reach this green endpoint before I can evaluate these 2 red edges. And then I need to reach this green endpoint before I can evaluate these 2 red edges, and so on, right? And so, in the early days, in the sort of very early days of SIDH, before it was even called SIDH, we would do this simply by sort of filling out all the branches in the tree, right? But then we quickly realized that you can play a sort of combinatorial optimization game and not fill out every branch in the tree. You can sort of, devise some sort of sparse tree, or where you don't have to visit every node. You do have to visit every sort of green node down at the bottom, but you don't have to visit every sort of node in between, and yet you can still get from here all the way to here, okay? And I've also suppressed from this tree sort of one more isogeny that would get you to sort of effectively, the R7 to get the degree 7, out of the 7th isogeny that you would need. Okay? So just keep in mind that, you're traversing a tree under these certain restrictions, right? That you can always take blue edges, the ones that go in the southwest direction, no matter what. But in order to take a red edge that goes in the southeast direction, you have to have unlocked the potential for that red edge by finding the corresponding kernel point down on the bottom row. Okay? All right. So, sorry, I'm not used to this pointing yet, sometimes I'll get things backwards. All right. So optimizations. How can we make this faster? So this first optimization is something that I call optimization 0, because it's something that you can always do. You just use smaller parameters, right? Now, of course, using smaller parameters has a cost, right? Which is that the security level will go down, right? I mean, you'll be less secure if you use smaller parameters typically. But in this case, we have a preprint from Goraj and I believe 3 other authors published earlier this year, which concludes that based on sort of a more detailed analysis of the actual sort of post-quantum security provided by SIDH. Now remember, more or less the whole point of SIDH is to get post-quantum security, right? That's the main motivation for all of this work. So under their more detailed analysis, they find that you don't actually need 751-bit primes in order to achieve a 128-bit security level. You really only need a 448-bit prime. And the reason for that savings comes down to sort of analyzing exactly how much it would cost to build a circuit that you need in order to do this sort of claw finding thing where you're doing like, 1/2 of it using Grover's algorithms so as to save yourself that factor of 1/3, getting down to 1/3 in the exponent instead of 1/2 and so on. And by the time they are said and done, they analyze this. It comes down to actually a similar story as what you found, what people have found earlier for hash functions, which is that sort of in the hash function case, sort of the purported savings of quantum attacks against hash functions for things like collision fighting, for example, don't actually materialize because existing classical algorithms are already good enough to sort of capture all of that speed up that you would get from the quantum case. All right, so their conclusion here is similar, except that it's not collision finding, it's claw finding. Okay? Now, if you believe this result, which I'm not going to make a claim one way or another as to whether or not one should believe this result, but if you do, then you're going to get your factor of 4 right back, right? Because when using something like, well, they had to go a little bit lower than 448. That's just because in SIDH you don't have complete flexibility to pick your parameters. You need parameters where certain products, of prime powers plus or minus 1 are prime, and well, they're just not that common. So sometimes you have to pick parameters that are a little bit off from what you want. But they did an analysis that if we were to use, say, 434-bit primes instead of 751-bit primes, SIDH would get about 4.8 times faster. Okay, so remember that factor of 4 from the first slide? Where is it? Over here. So remember that factor of 4, even with improvement by a factor of 4? Okay, we got our factor of 4. Okay. All right, so now let's go back to this thing. I'll take this as sort of some starting point. This is not the end point. That we still have more optimization to do, right? But just to give you some idea, of where I think that hopefully by the end of this talk I can convince you that at least in some cases SIDH might be something that you want to think about even when you're working on an embedded platform. Okay. All right. So what else can you do? So this is again prior work, and maybe I should mention that much of what I'm going to talk about today is not actually my work. It's sort of work. There are a few results that are partly my work, but most of it is just sort of me collecting results from other people and putting them together, which I guess places me solidly in like old fogey territory or something like that. I'm not sure if that's a compliment or an insult, but be that as it may. I'm mostly talking about results that other people have presented. Okay, so a couple years ago, there was a result published in Cannes 2016. This one is partly my work. I am an author on this work by Brian Koziel and various others, which indicates that you can use SIMD instructions to speed up SIDH, right? Now, in this context, when we talk about SIMD, we're talking about 32-bit ARM platforms, so that would be like neon instructions for ARM. Now, whether or not this qualifies as an embedded platform is something that is possibly up for debate. You might say no, it's too powerful. But in any case, it's just a little way to get started and to sort of indicate where those savings might come from. Okay. So SIMD is, as we all know, stands for single instruction multiple data. It's a way to sort of vectorize instructions, right? So you can multiply 4 things by a single factor instead of multiplying them, do 4 multiplications one after the other. You can do them sort of all at once. And the way that you do this is you need sort of slightly wider registers so as to be able to multiply one block into 4 blocks all at the same time. And you also need special instruction set extensions to let you do all of this stuff. The sort of reason why SIMD is not simply just parallelism period is because you have some restrictions in SIMD. It's single instruction, multiple data, but that doesn't mean that the multiple data can be sort of arbitrary data. It has to be sort of related to each other in some way. And for multiplication, which is largely one of the bottlenecks in SIDH, the restriction is that when you're doing SIMD multiplication, you can multiply 2 things, B and C, for example, by a common factor A. Right? So you can multiply A times B and A times C and get both of those results at once. But you couldn't do like A times B and C times D and get both of those results at once. In order to do that, you would need like 2 separate multipliers, and you would just need separate instruction units. That would just be parallelism. Okay? So what we do in our work, so our strategy is that our numbers are big enough that when we're doing these multiplications, we can actually take advantage of SIMD even within what to the higher level protocol is considered a single multiplication, right? So a single multiplication might be multiplying 2, 500-bit numbers or 700-bit numbers together, right? But when you're working on a processor with a 32-bit word size, then even multiplying 2 single numbers together of that size involves lots of little multiplications, and a lot of those little multiplications involve sort of the same factor on one side and different factors on the other side, which is exactly the kind of situation where SIMD helps. Okay? So that's what we do. Let me try to get the direction straight here. Okay, so here's just a sort of small illustration of how this works. So what we're doing here is we want to multiply, in this case, a single 256-bit word by a 32-bit word, right, for example, right? And the way that I've sort of numbered this notation is that the A register is my large 256-bit word, okay? And each block here is a 32-bit word, right? So there's 32 bits, 32 bits, 32 bits, 32 bits. You add this up, this is 128 bits, this is 128 bits. The SIMD stuff on ARM works through 128 bits at a time, so that's what we're going to use here, okay? The first thing that we do is we sort of rearrange our digits in our 256-bit words. So we take so we break it up in half, and then we take the 32 least significant bits of each half and squish them together over here, and then the next actually we skip one, and then we take the next 32 bits, and then we smush them over here, and then we put the gray stuff over here and the white stuff over here, okay? And then when you want to multiply, this stuff by B0 is your 32-bit word that you're multiplying this by. Okay, so here the notation is that this 64-bit block is A0, which is over here, times B0, which is over here. And that gives you, this is 32 bits, this is 32 bits, that gives you 64 bits, right? And then this 64-bit block over here is A4 times B0, that gives you all the stuff over here, okay? Now when you do this, there's a possibility of a bit sort of overflowing, that's your carry bit, and so if you have a carry bit, then that bit for A0 would influence the A1 result, for A4 it would influence the A5 result, right? And so your SIMD sort of speed up occurs sort of essentially here, right? You're multiplying two things by B0 at once. Now you could conceivably speed this up even more if you had even larger registers. For example, all these things are being multiplied by B0, right? A0, A1, A2, A3, A4, A5, A6, A7, they're all being multiplied by B0. So if you had the space for it, you could do sort of more instructions at once. It's just that ARM doesn't have the space for it. 120 bits is as much space as you're going to get, right? But do keep in mind that on other platforms, such as x86-64, for example, you can sort of slurp in up to 512 bits at a time, depending on what instructions and what version of processors you have. So in those cases, you need, this is where sort of a lot of the speed up comes from. Even in software, forgetting about embedded systems for the moment, like even in software, when you're doing this, SIDH really benefits from wider data paths and more SIMD. Okay, so that's why when every time a new Intel processor comes out, like when Haswell comes out or Skylake comes out, I'm like, yes, because it's going to make SIDH faster. Okay. Anyway, you carry all these bits and go over here. There's one more carry bit, which is the result of A3 times V0. That will give you a carry bit for A4 times V0. It goes over here. Unless you are incredibly unlucky, this carry bit will not propagate all the way over here and affect anything else. Okay. So you just have to sort of take care of that one extra bit. Okay. So optimization, what I call number 2, something that was published this year, or will be published this year, Aaron Hutchinson and Koray Karadina. Again, in their work, they mostly focus on software, but this same principle also applies for hardware, as we'll see in just a moment. Okay? So their idea is that when you're doing this sort of combinatorial optimization along the tree, right, what you can do is you observe that. Remember, southwest is free, southeast is sort of not free, it's constrained by the need to reach the leaf node on the bottom row before you can go southeast. Okay? So that was our basic structure of SIDH computations. Now, when we were doing this before, like let me back up a few slides here. When I'm doing it sort of in this figure, for example, I'm optimizing it so that I minimize the total number of edges, right? Under the theory that each edge has to be executed once, and there are some dependencies among the edges, like you have to do these edges first before these edges, but it doesn't matter sort of in terms of the total time that it takes, which edges you do first and which edges you do second. But when you're talking about parallelism, then it kind of does matter, right? Then you have to keep in mind sort of the order in which you can perform these operations. So this slide, by the way, is borrowed from their PQ Crypto rump session from this year, where Aaron Hutchinson presented this work. I'm certainly not trying to claim credit for his work, but here's I give the citation for that purpose. But the full paper appears in IndoCrypt. What they do is they set it up so that if you have more than one sort of processing unit or instruction unit that you could use to sort of perform two multiplications at once, let's say, instead of one multiplication at once, then the calculus of sort of optimization in this diagram changes quite a bit. Okay? And in their example, you observe that when you're going southwest, when you're going from this node all the way down to this node, for example, there is, as far as I can tell, no opportunity for parallelism there. You have to do this before you do that, you have to do this before you do that, you have to do this before you do that, and so on. You have to go all the way down from the top node to the bottom left node, and you can't speed that up using parallelism. But once you get down here, now you can do certain steps in parallel. Right? In particular, what you can do in parallel is you can do this edge, this edge, this edge, and this edge. You can do all four of those independently. Right? It doesn't matter which one you do first. None of these results depends on the none of these computations depends on the result of any other of these computations. Okay, and so what they do is they structure these results in such a way so as to take advantage of more parallelism in the southeast direction than in the southwest direction. And so you see here that there's quite a bit more edges in the southeast direction than in the southwest direction. And if you were to add up all of the edges, it would be slightly more than the exact optimal number of edges that you could get if you were really trying to minimize the sum of the number of edges regardless of direction. But here, the southeast directions, they're not free, but they are free in a certain sense, in the sense that you can sort of, if you have two processors, you can run two of them at once without any extra sort of latency cost. It does cost you more in power budget, but it doesn't cost you any more in time latency, right? So they structure this computation in such a way that you're going to, let's say, this example is optimized for, let's say, k equals 2, right? So you can do two of these southeast edges. You can do any two of these southeast edges at the same time, right? So let's say you do these two at the same time, and then you do these two at the same time, okay? And now you can do these two and then one of these. And then now you need another long serial computation to get down to this edge. This node, sorry. Once you get down to this node, you do like these, and these at the same time. Then you do these, and these at the same time. Then you do these and these at the same time. Then you do those at the same time. You need one more computation here. Then you do these two at the same time, those two at the same time, one more thing, you do those two at the same time, and so on. Right? And so they implemented this sort of on sort of in software. And they found that these are percentage speedups. Okay, so these are not. It's not that it's 30 times faster. That's unreasonable. It's like 30% faster. Okay? So that's what they found, sort of in their work. The other sort of approach that you can take to optimization, rather than the stuff that I've been talking about so far, which I would regard as pure software or taking advantage of just the hardware facilities that are already sort of present in general purpose CPUs, is you can design your own hardware, right? And so I'm going to talk a little bit about sort of some earlier work on this slide, and then I'll talk about sort of the latest and what I consider latest and greatest results in this regard. The earlier work that I'll talk about is there's a series of papers by Brian Koziel, Reza Zargarash, Mehran Mozaffar Kermani, and somehow my name is in one of these papers. It's a series of papers on implementing SIGH using sort of custom hardware. And by custom hardware, we mean FPGAs, although you could also do this on sort of even more hard-baked hardware, such as ASICs, for example. The source code for all of this work, well, not the most recent work, but the source code, I believe, up to this level is actually included with the NIST submission to Psych. If you go download the sort of source code that is packaged with the NIST submission to Psych, you can find in addition to the sort of standard software implementations that are required as part of this process, we also have a hardware implementation, which can be compiled into your FPGA or ASIC, depending on your preference, which written by Brian Koziel. Okay, so yes, Brian Koziel is sort of a one-man wrecking crew as far as SITH hardware implementations go, and he's not even a PhD student. Keep that in mind. Okay. What do you do? Well, it looks like this. I mean, it's these sort of, I don't even know if you can read all this stuff. So the way to read this is, so here's this thing on the right is sort of a high-level diagram of how to implement an isogeny computation using multipliers and also adders and subtractors and various things like that. So it's kind of what you would expect. If you're writing it, in software, you need to get, like, I don't know, this expression over here to implement sort of the kernel of an isogeny, and of course you're going to build that up using sort of individual arithmetic operations, and each of those arithmetic operations is no longer a sort of assembly instruction in software. It's going to be sort of a circuit that you build using transistors in your FPGA hardware. Okay? The sort of layout is sort of motivated by the sequence of operations that you're going to need in order to compute an isogeny, in whatever field size you want to compute it in. And then on the left side here, we have the architectures for, respectively, this is the sort of multiplier, I believe. This is a part of a multiplier. This is a part of a part of multiplier, and so on, and drilling all the way down to the bare transistor level. In FPGAs, you can take advantage of parallelism, as you would expect. And oh boy, can you take advantage of parallelism, because you don't even have to shuffle data around, right? If you want to sort of do something, if you want to do 3 things to one piece of data, you just need 3 wires. You just move the data around using wires. It goes at the speed of light. You don't even need a clock cycle for it. Right? If you want to multiply 3 things, you can just sort of build yourself 3 multiplication units. I mean, it'll cost you in terms of chip area, right, to build all those transistors, but it's not going to cost you anything in terms of speed to do 3 things at once instead of 1 thing at once, because all the things that can run sort of exactly in parallel. You can lay out your hardware exactly how you want. Okay. So the basic thing that you can do is sort of FP squared multiplication becomes sort of just as fast as FP multiplications. If you want to spend sort of the hardware and transistor count to implement 3 multipliers instead of 1, right? Which of course you should, because that's the whole point of doing this in hardware, right? Because when you're doing an FP squared multiplication, let's say you're doing it with Karatsuba, then you're going to need to do 3 multiplications, right? To do 1 FP squared multiplication, but those 3 multiplications are independent of each other, right? So you can just sort of do all 3 of them at once using 3 multiplier units. You can perform isogeny evaluations in parallel. So just as in the Hutchinson and Carabina work, so in this diagram, right? So in this diagram, I talked about how you could do this sort of stuff in parallel, where you can do 2 isogeny evaluations in parallel. Well, we already did that. We actually already figured that out. I'm not disparaging their work. I'm just saying that we had already figured it out. The timing is worth noting, I guess. So this quote is from Brian and Reza and Mehran's 2018 paper, which was published in March, and I believe Hutchinson announced his result in April at PG Crypto. So the timing is such that it's probably quite reasonable that the 2 things were developed independently. So this is not like from 2016, for example. Okay. But yeah, you can do the same kind of thing in hardware, right? So in hardware, you just in hardware, it's actually easier than in software. You don't have to lay out you don't have to shuffle the data around. You can just lay out the traces to sort of do exactly what you want, right? And so what we get is what they get in hardware is they get a 53% speed up. Oh, hey, that looks kind of close to the kind of speed up that the other group got. What did they get? 30%? 55%. Yeah, 53% speed up. But when you're talking about this, there's a discussion they have to have, which is how many multipliers do you allow, right? I mean, you can go really crazy with this stuff. You could have hundreds of multipliers, but at some point you hit the point of diminishing returns. Okay. All right. So for some results in this area. We have, let's see, so we have, I'll just sort of jump to the headline result here, 16.5 milliseconds for a full round of key exchange. This is 4 SIDH sort of basic operations, 4 kernel computations, not 1. Okay? So each kernel computation runs you about 3 milliseconds at a 200 megahertz clock speed. If you want to compare it to New Hope, you're talking about something like 4 times more chip area. It's 4 times larger, it's 10 times slower, but the keys are 6 times smaller, right, compared to a hardware implementation of New Hope. The bottleneck ends up being finite field exponentiation, which you need for a few inversions, but it's like the one thing that you can't speed up using parallelization, because you have to do square multiply, and there's sort of serial dependencies there that you can't wash away. Okay, so the last thing that I want to get to is this recent work by Jeffrey Calhoun. It's a master's thesis entitled Optimization of Supersingular Isogeny Cryptography for Deeply Embedded Devices. And so here's what they find. So the contrast here is instead of using, instead of designing a full FPGA chip that implements all of SIDH in hardware, the approach that Mr. Calhoun takes is to use a software processor, but augmented with sort of hardware coprocessors for things like finite field arithmetic. And to make sure that we're not sort of overly optimizing things for SIDH, just to see what we can get if we don't do that, what he does is he uses existing finite field arithmetic coprocessors. In other words, things that were not specifically designed only for SIDH, or things that were used previously for elliptic curve arithmetic. And he takes those and sort of runs the software on them to make them do SIDH and sees what we can get. And what we can get is actually quite noteworthy. You can get on a sort of standard embedded processor, real embedded processor like microcontroller type stuff. If you allow yourself some instruction set extensions on your main processor, you can get already a 6 to 7 times speed improvement. This is a factor of 6 or 7, not a percent. Okay? And if you allow yourself furthermore a co-processor, not just instruction set extensions on your main processor, but a separate co-processor dedicated specifically to finite field arithmetic, then you can get a further 6 times speed improvement. Okay? Again, that is a factor of 6, and it stacks with this improvement. And if you take the existing finite field coprocessor and you modify it slightly to make the data path wider, because if you were designing it for SIDH, you would do exactly that. So he's not, there's no big changes here other than just making the data path wider. Okay, all the control logic and everything is exactly the same. So if you do that, then you get a further like 3 times speed up. Okay? So you can get all of this, certainly the first 2, and maybe arguably the third, all of this comes using just existing designs. There's sort of nothing that you need to do to make things work, especially for SIDH in any way. So the platforms that he targets in his work, he calls them PEAT, PEAT-ISE, PM32, and PM64, and these stand for the following things. So PEAT is a it's a special purpose sort of RISC processor using the MIPS instruction set. It's sort of pretty similar to what you would find sort of in your standard IoT device. It's like the same processor class, let's say, as ARM Cortex M4, probably even M0. It's a little bit slower than the M4. There's PEAT-ISE, which is this CPU with the instruction set extensions for prime field arithmetic. There's what we'll call PEAT with Monty. Monty is the FP field arithmetic accelerator, and then there's the PM64, which is the same thing but with the accelerator modified for 64-bit word size. All of this was originally designed for traditional ECC. It was not designed for SIDH. Okay. And by the way, the reference for all of this earlier work is a PhD thesis by, I believe, Andrew Targeta, called The Design Space of Ultra-Low Energy Asymmetric Cryptography. Okay? So here are the results that we have. On the top line, is the paper that I started with in this presentation, the 18 seconds to key exchange, right? This is where you're talking about 1 billion cycles, sort of to get to one SIDH key exchange, right? The second part of this table is Calhoun's results. Okay, so starting at the top, Pete is the unmodified processor. You're running it in pure software. This processor, as you can see, is actually a little bit slower than the Cortex-M4. It's a factor of 4 slower per clock cycle. But once you add instruction set extensions to the mix, it already becomes faster than the Cortex-M4, despite having a slower sort of central processing unit. When you get to the sort of realm of hardware field acceleration, then these numbers go way down, right? And they go with the 64-bit data path, they go way down. These numbers are actually comparable on a clock-for-clock basis with x86 software implementations. You need a little bit of hardware for this. You don't need like a full-blown FPGA implementation of SIDH. You just need sort of a little bit of FPGA acceleration for your finite field arithmetic, right? With a 64-bit word size. Okay? In Calhoun's thesis, he actually asserts that Pete with Monty 64-bit data path is faster on a clock-for-clock basis than x64. The reason why he got these numbers as faster as those is because he wasn't using Skylake architecture. If you use Skylake, then the numbers go down to what is cited over here. Okay? And just for fun, I've also thrown in the numbers that you get on a clock-for-clock basis using the full-blown FPGA implementation. So you see that then 27 goes down to like 1 or 2 or something like that. Right? So full-blown FPGA is still going to be quite a bit faster. But it takes more chip area, right? That's the whole point. Specifically, here's the chip area. Here's the sort of count of all the chip area stuff. So on the top, I have New Hope, right? And so you can see here, New Hope takes. You need a glossary for all this stuff, like flip-flops, lookup tables, digital signal processing slices, and so on. The way to read this table is that flip-flops are basically your sort of what we think of as arithmetic sort of gates. Lookup tables are like sort of fixed logic tables that can perform. They can evaluate fixed functions. Let's say BRAM is the equivalent of RAM. So the RAM doesn't actually cost too much. What you're looking for is sort of lookup tables, and especially flip-flops. Those will cost you a lot. Right? So you see that a full-blown FPGA implementation of SIDH costs you quite a bit more than New Hope, but if you're doing this sort of finite field arithmetic acceleration, you don't need that much hardware acceleration. You just